Excellent. All right, we're keeping things moving along today with our perceived session. I want to welcome everyone who's tuning in right now to our session on neural network pruning for compression and understanding. My name is Trey Pierce. I'm the lead solution engineer here at Clarifai, and I will be moderating this session today. Before we get started, just a bit of housekeeping. You might have heard already before, but all attendees will be muted, but we encourage you to ask any questions, which you can do by typing into the Q&A or the chat here on the right-hand side of the screen. We will answer all questions after the session, which should last roughly about 30 minutes, give or take. Just a note that today's session will be recorded and will be available on demand after the event. I couldn't be more excited to be introducing our accomplished session speaker, Dr. Paganini, who will be sharing some of her wisdom on the critical topic of neural network pruning. But before I do, just want to give a little bit of background on Clarifai for those needing a bit more context on today's conference. Clarifai is a leading independent provider of deep learning technologies and services. Our end-to-end platform enables our customers to train and deploy computer vision and NLP models, helping to transform untapped, unstructured data into insights and actions. Founded in 2013 by former ImageNet Award recipient Matt Zeeler, PhD, we've since added more than 80 employees with offices in New York City, San Francisco, Washington, D.C., and Tallinn, Estonia. We've received numerous awards by industry observers, including Forrester, who recently recognized Clarifai as a leader in the rapidly emerging market for computer vision platforms. Okay, with that out of the way, I'm excited to have the honor of introducing our distinguished speaker today for today's session. Dr. Paganini is a postdoctoral researcher at Facebook AI Research, FAIR is the acronym for that, in Menlo Park, and an affiliate at Lawrence Berkeley National Lab. She joined Facebook in 2018 after earning her PhD in physics from Yale University. During her graduate studies, she worked on the design, development, and deployment of deep learning algorithms for the ATLAS experiment at CERN, with a focus on computer vision and generative modeling for particle discovery and scientific simulation. Prior to that, she graduated from the University of California, Berkeley, with a bachelor's in physics and astrophysics. Her current research focuses on empirically characterizing neural network properties and dynamics in the over-parameterized and under-parameterized regimes using pruning as a tool for model compression. All right, with all that said, I'm going to go ahead and hand things over to Dr. Paganini, who will be leading today's session. Michela?
Yes, hi everyone. Thank you so much. That was a brilliant introduction. It's absolutely a pleasure to be speaking here at Clarifai Perceive. So today I want to take you on a little journey through some of the recent work in neural network compression, both from the practical and the fundamental research standpoint towards A, efficient AI models, but also B, a more principled understanding of the inner workings of neural networks. So over-parameterization is behind the success of modern deep learning. Of course, this has been enabled by a lot of groundbreaking advances in both hardware and optimization, but today I want to focus specifically on the idea of over-parameterization itself and its connections with pruning, so as a consequence really of the dynamics that it induces. And as you well know, many of the state-of-the-art models in AI research, especially natural language processing, are based on extremely deep neural networks that are able to learn in a way or another without insurmountable difficulties that are conventionally associated with their depth and with over-parameterization. And indeed, as you're all very much aware, I'm sure, neural networks have been massively growing in size over the past decade, with some of the newest state-of-the-art models getting into over 500 billion parameters these days. And models are getting bigger with no sign of slowing down. But despite this push towards bigger and increasingly more powerful models, there have been competing needs of fast deployment and efficiency that have spurred the community to simultaneously focus on the other scaling frontier, so the frontier of efficient AI. And so when looking at large language models, for example, rarely do researchers or even companies have the luxury to waste compute cycles on retraining redundant weights and then deploying them because of bandwidth limitations, perhaps. So in practice, what happens is that practitioners have begun focusing on model compression methods such as pruning and quantizations, and have consistently empirically demonstrated that training a huge model and then compressing it down always beats training a smaller model from the get-go. And so to that end, several groups of efficient model design techniques have been proposed over the past years. And I'd like to divide this space into constructive approaches and destructive approaches to efficient model design. So constructive approaches try to build an efficient architecture from the ground up. So they carefully add and position parameters and operations in clever ways, either through human ingenuity, so human design, so explicitly adding our inductive biases and transformations that we know to be important for the task into the network, or automatically, so in a neural architecture search or AutoML type of way. And you can put all sorts of things in here, starting from the basic concepts of weight sharing all the way to the development of architectures like ResNets or squeeze nets, and even some of these randomly wired neural networks that are becoming popular these days. But then there are the destructive approaches to intelligent model design, and these are the ones that I've personally been focusing on, and these include knowledge distillation, for example, from a teacher network to a smaller network, quantization of the weights in a network, tensor factorization techniques, and finally model pruning, which is what I will focus on today. So what is pruning? So simply put, pruning just means removing unnecessary stuff from a network to try to reduce it down in size. Now, of course, that's a very vague definition. What type of stuff, what type of structure are we talking about? Are we removing neurons or just connections between these neurons? And how do we tell what's unnecessary if we don't really have a robust theory of how things work inside of networks? And so pruning, thankfully, has been used as a model compression technique in machine learning for multiple decades. So there is prior art, starting from the literature on decision tree pruning and then to early work on neural network pruning with papers like the optimal brain damage and the optimal brain surgeon, for example, just in the context of generalization and interpretability and more. And so over the years, researchers have come up with many different ways of identifying superfluous portions of our models. And this has resulted in the creation of a variety of different pruning algorithms. And ultimately, these might vary across several axes. And some of these axes include the nature of the entities to prune. So are we pruning connections, nodes, or even channels or entire layers? And the choice of proxy for importance to evaluate on each entity. So the weights associated with them, or the activations or the gradients, and the group of entities to pull together for comparison. So are we comparing all the units in a layer or all the units in the entire network? When are we pruning them? During, before, after training? Are these pruned entities pruned forever, or can they be reinstated at a certain point during the training loop? Are we applying hard pruning, so binary masks, or some sort of soft pruning, iterative or one shot? And what do we even do with the network once it's been pruned? Do we fine tune it? Do we reinitialize it? Do we rewind it? And so on. And so let me help you visualize this a little bit better. So normally when we are in the business of building a new network from scratch, we first initialize it, and then we train it according to some procedure. Now, when we look to adding pruning into the process, most of the pruning techniques historically have acted on pre-trained networks, so after the training phase. And after pruning, usually the net isn't just left as is, but it is fine-tuned or partially trained again. And this can even generate a loop of training, pruning for a certain number of iterations. And by the way, this iterative pruning and fine-tuning technique has been the leading procedure up until very recently. And then another thing that one can do is to extend the reach of this loop. So instead of simply continuing training the net after pruning, one can decide to rewind the weights in the prune model to their initial values at initialization, and then retrain from there and then prune again, perhaps in an iterative fashion. And so this is exactly what the lottery ticket hypothesis, at least in the original formulation, advocated doing. And I'll tell you more about what that is. But first, okay, just an aside to something that unfortunately I won't be able to get into as much today, but just for completeness, I want to mention that there are also methods in which pruning happens at initialization, so prior to training, and this can be one shot or iterative, and so the network can be compressed before it's even trained. And of course, there are also other methods that train and prune simultaneously, perhaps by imposing a sparsity-inducing regularization or something of that kind. And then another important dimension along which pruning techniques might fundamentally differ is whether they prune entire channels or units, and these are called structured pruning methods, or individual connections only, and these are called unstructured pruning methods. And here we have a nice visual representation of the difference between the two in terms of the weights that remain in a simple convolutional layer in this case, in the unstructured and the structured case on the right. And so you can see how the connectivity patterns totally change. So this can have profound consequences in the implementation side of things in terms of what's easier to implement on hardware. But unfortunately, there's always a trade-off in terms of the robustness and resilience of networks to certain kinds of pruning. So now whether you perform structured or unstructured pruning, there are also different criteria that you can use to select which weights to prune. And this will give us different subnetworks, of course, with different characteristics. And the selection could be based on any fancy or non-fancy function of the weights or the gradients or the activations or some interpretability measure, really anything. And there's this great paper from Uber, for example, where they tried to implement different functions of the weight magnitude. And in general, I just wanted to point out that the most popular pruning technique simply consists of removing the small magnitude weights in absolute value at convergence. But we'll revisit this later. So let's see how this is used in practice. So why should we care about compressing models? So my number one reason personally is for sustainability, but of course there are many other compelling points that can be made about the future of AI being ubiquitous and the need to target resource-constrained scenarios with a global perspective in mind as well. But more concretely, for many AI startups and teams, the question is always, where and how does my AI model or application run? So if you're running on public cloud, you likely care about identifying reducible operational expenditure inefficiencies. If you're on premises, then you probably care about lengthening the useful lifetime of your hardware. And so with pruning, you can make sure that as models get bigger and bigger and more complex, you'll still be able to run them on your hardware wherever the state of the art will be in 5 years. And then if you have on device or on edge as type of use cases, you might need to ensure slim memory, slim compute, and power footprint. So these are obviously top of mind. And compression can enable compute and memory savings, potentially both at training and at inference time, to capture some of the latest features that you might find in the data. And it can reduce latency for real-time applications. It can allow models to live on device, on the edge, so on mobile or devices like VR goggles like Oculus, IoT systems. And this can also begin to address some of our privacy concerns, for example. And then there are power and energy savings arguments to be made as well, so battery, heat dissipation. And finally, from a scientific standpoint, I think what stands out to me is that this gives us a way to understand what parts of the networks are responsible for learning. And these are just some of the advantages, but of course, there could be disadvantages as well, such as the absence of good pre-trained compressed models, and then the fact that the ideal sparsification might be task or hardware dependent or objective dependent in general, and it can also be very computationally expensive to obtain. And then one more thing is that, of course, general purpose hardware is optimized for dense computation. So we often need to rely on custom hardware or custom logic to take full advantage of compressed models. And to that end, people have started developing hardware-oriented compression techniques, including load balance-aware pruning or locality-aware pruning, to try to reduce the data movement and expensive lookups. So while we're on the subject of pruning, let me just take a quick detour to tell you more about the pruning functionalities that I personally contributed to PyTorch, the deep learning library, and you can now just find and use out of the box in the library itself. And later I'll flash a few recent research results that have been enabled by pruning, but none of that would have been possible without robust software tools to power our research questions. And so I'll just go into some slides to explain the internals of PyTorch pruning, as well as the surface area that you would interact with if you were to use this. But then I'll also leave you with some of the tutorials to look up in the end. So just as a quick overview, pruning methods that are currently available in torch.nn.utils.prune are listed here on the right, and they're all derived classes that inherit from base pruning method. And that's because what changes from pruning method to pruning method is just the logic that tells us what is being pruned. But after that has been figured out and identified, then handling the pruning itself and applying it correctly is something that can be centralized and can be abstracted away into a base pruning class. So we have this base pruning method that enables the creation of new pruning techniques by simply requiring the override of methods such as compute mask, which is what handles the creation logic for the mask that ends up powering the different pruning techniques. And in practice, pruning in PyTorch is implemented like a reparametrization of the prune tensor in terms of the original tensor and the prune mask, which is just a binary mask of zeros wherever the weights are pruned and ones where the weights are kept. And so we don't physically remove or drop connections or neurons. We implement it as a reparametrization, and then the base class takes care of storing and fetching all of these different objects so that you can always have the prune tensor available to you at train or test time. And to implement iterative pruning correctly with each call building on top of the prior pruning calls, we have this object called the pruning container that stores the history of these calls and is able to combine them and apply them correctly while keeping track of all of the masks that have been produced before. So PyTorch pruning was designed to be very modular and extensible beyond all of the techniques that we already implement out of the box. So it enables researchers to express pruning ideas very quickly in a common language. And hopefully it's also very easy to use. So just with one line of code, we can prune a layer in a network, we can enable iterative pruning, and we can even prune globally across the whole network. And as a researcher, the important point here is that there are no changes to your model definition or to your forward call. And so this was just a brief overview of these methods and these functionalities that have been available in PyTorch since version 1.4. And you can find the code on GitHub on the first link on the left, and then some more instructions and tutorials on the right. Okay, so now that we have all of these tools and this knowledge of pruning, let's finally get into some more advanced AI research topic, as well as some of the ongoing research in this space, which will leave us with more open questions than answers, but that's research. So we've certainly seen so far the success of big overparameterized models in AI. And the question now becomes, is overparameterization really needed, or is it just convenient somehow to train our models? We know for a fact that it's not necessary after training, but is it really necessary even during training? Or can we perhaps find some smaller networks with similar benefits and some similar characteristics? And this is exactly where the lottery ticket hypothesis paper comes in. So what's the lottery ticket hypothesis? What does it say, and why is it so important? So this work is famous because it provided empirical evidence that demonstrated that certain small, sparse networks can be trained from scratch, so from initialization, to very competitive performance despite their very, very low number of parameters. And this goes against the usual notion that we have that networks with fewer parameters aren't as powerful and shouldn't be able to train and reach the same levels of accuracy or performance as networks with tens or hundreds of times the number of parameters. And so this work also provided an algorithm to find these lucky sparse subnetworks. And this consists of iteratively pruning and rewinding to the initial parameters a regular overparameterized architecture that you would start out with. And rewinding to the initial values is really the key idea here. And they show in this paper that it works better and it gives consistently higher accuracy for the same level of sparsity compared to continued training, meaning just fine-tuning as we defined it earlier. And the hypotheses of the authors is that there always exist small networks of this variety with fewer parameters that are able to train from initialization to state-of-the-art performance, but they are really hard to find, really hard to identify. And the analogy is that they're as hard as winning the lottery, and that's why they're called lottery tickets. But with overparameterization, the theory says that we are essentially buying ourselves more tickets to this lottery by sampling combinatorially many different subnetwork combinations within the larger model. But the problems are that A, we don't fully understand why this is the case, and B, this iterative pruning technique that the author suggested is quite expensive from the computational standpoint. So it is also computationally hard to find these lottery tickets. And so, of course, This raised a lot of questions, and I tried to set out to answer some of them with my research. And first of all, of the two contributions of the original paper, so we have the observation of the existence of lottery tickets and the proposal of the algorithm to find them, we really started picking apart the second part, so the algorithm, and we started asking whether there was something special about it, or whether other pruning techniques, so other than this iterative magnitude-based unstructured pruning that they used, were able to find winning lottery tickets. And so here we tested some of the random and magnitude-based and global and layer-wise and structured and unstructured pruning techniques that I told you about that are now part of PyTorch. And so on the left, we see the test accuracy as a function of the prune weights for a series of different pruning techniques, color-coded. And what you can see in practice from this plot is that, yes, there are very many different pruning techniques that are capable of finding competitive subnets that train to high accuracy all the way up to high sparsity levels. And so we asked, well, do all the pruning techniques find the same winning ticket, or are there many different ones within the same base architecture? And so the answer turned out to be that each pruning technique ends up finding slightly different lottery tickets. So there is more than one lottery ticket inside of a big network, and we should be careful before we dive into overanalyzing the properties of one type of lottery ticket without understanding how it fits into the broader picture. And so in fact, this is kind of what you see here on the right. This plot shows the Jacquard distance between the subnetworks, which is related basically to the intersection over union of these binary masks. And you can see how it grows as the sparsity increases. So these masks become more and more divergent. Another thing that we noticed, so in this work, we started seeing an interesting pattern when we looked at the unpruned weights, so the weights that remain. And if you look at the top center versus the top right image here, what perhaps unexpected advantage of rewinding the weights to the initial values after pruning, as suggested in the lottery ticket hypothesis paper, as opposed to fine-tuning them, which is what has always been done before, is that unstructured pruning patterns now tend to look very much like structured pruning patterns, which I put for reference on the left side. And so we have these weights that survive that are displayed along only a few channels instead of what happens when you fine-tune, where you get a sparser, more unstructured pattern. And this is true across a variety of different architectures as well. So this could be advantageous if structured patterns indeed are preferable for hardware considerations and hardware implementations. But this is a phenomenon that we would have to explore a little bit further. Okay, so far we've determined that there exist multiple winning tickets with different properties depending on the pruning method that one uses. But what about lottery tickets that are found with the same pruning technique but on different data sets? Can I successfully train a lottery ticket that I found on one task now on a different target task? And again, the answer turned out to be yes. We find that these lottery tickets seem to be relatively transferable in the sense that they can be retrained from scratch on a different task within the same domain, of course, but without always having to source a new one with this expensive pruning, iterative pruning technique. And so another thing that we notice is that tickets that are sourced on harder tasks like ImageNet tend to transfer better on easier tasks than vice versa, as one would imagine. But the importance of this observation is that having to iteratively prune a new model for each new data set that you're interested in might have severely limited the promise of these sparse networks and the utility of them. And so this work instead shows that there is some promise towards being able to find, as we call it in the paper title, a lottery ticket to win them all. So one that could be used across a variety of different tasks. So once again, we asked, okay, is this transferability property, is that because lottery tickets that are found on different data sets are essentially identical? So do they just trivially transfer? And the answer here is no. So these masks that define the sparse connectivity of these subnetworks that we find on different tasks are actually quite different. And the distance between them grows as the sparsity grows, as we've seen before. This is plotted here in a different format, but that's the same idea. And then one would naturally ask, okay, do these masks completely diverge? Do they separate out completely? So let's zoom in for a second. So this is a set of very high sparsity networks. So iteration 19 of pruning corresponds to 99% of the weights having been removed. And so the number of remaining weights is very low for some of these smaller networks. It's in the hundreds in the entire network. And yet we see that these masks are not completely non-overlapping. There's still some overlap, even at such high sparsity. And this sort of, we thought, identified a core, a shared part of the network that always goes unpruned regardless of this list of tasks, always across these. And so we decided to look into that a little bit more. And what we found is that the core part, so this intersection of masks that are sourced from different tasks, is itself obviously a sparser subnetwork, but it can train to high levels of accuracy. So by definition, it's itself, if we want, a lottery ticket. And one practical advantage of this observation is that we can use it to shortcut the way that we get a high sparsity lottery ticket. So the original iterative pruning algorithm was very sequential in nature. And this thing instead can be parallelized. So instead of finding a high sparsity network through, say, like 20 successive iterations of pruning, you can now find low sparsity subnetworks over multiple tasks, say with 2 only pruning iterations each in parallel. And then you can take your intersection and you can get a new high sparsity ticket. And the intersection we show is capable of achieving similar performance to equal sparsity traditional lottery tickets, even on some of the tasks that it was not sourced on. And it also appears to have some more advantageous properties from the trainability standpoint. And this can be shown by showing, for example, as I do in this slide, that the remaining weights, so the weights that go unpruned, are not as far from zero at initialization as the weights that remain in normal lottery tickets. And there's obviously a lot of work being done in understanding the properties of a good initialization strategy. So some interesting extensions at this point of this work that are both ongoing and potentially future involve using graph theoretical arguments to try to study the properties of this intersection network, to try to verify, for example, if asymptotically it stabilizes with the number of tasks that are added to the intersection, or if it stabilizes asymptotically with the number of training iterations that are performed. And so I think the real significance of this, to kind of revisit the title that we give to an earlier paper, is to really try to find this one ticket to win them all that can hopefully generalize. And this is, of course, a work in progress that will need to be confirmed. But there is another interesting dimension to the conversation that I think is oftentimes overlooked and that I would like to really stress in this case, and that's the dimension of responsible AI. So most papers, I would say, in the pruning literature, compression literature, usually assess the viability of a compression method primarily in terms of the trade-offs of total accuracy for increased sparsity, or flops per watt. But rarely do they investigate what any drop in total accuracy really means in terms of the classes or the individuals that get affected. And especially this is true when we're talking about deployed models, of course. But what if this intervention, pruning, severely affects the fairness of a sparse model? And so in this prune responsibly paper, we set up many large-scale experiments in the context of image classification, and I list all of the different factors that we vary across all of our various experiments, and all of this variation ultimately gave us about 100,000 different models to analyze. And what we looked at was the per class accuracy of these models. So to see if there were any disparities in the way classes were being treated based on some class characteristics. And so we hypothesized, as one might do, that underrepresented classes, as well as more complex classes or more diverse classes or outlier classes in your data set, could experience larger drops in performance after the model is pruned. And so we formulate these hypotheses and we test whether the magnitude of these effects was consistent with 0, so it was not there ultimately, or not. And we do so by controlling for multiple other factors of variation, such as the model type, the data set type, the pruning technique, the data set, the architecture, all of these things. And so we design ultimately a linear model to fit this per class accuracy as a function of all of these variables of interest and nuisance parameters. And we were ultimately able to reject the hypotheses that representation and class entropy and overall class difficulty had no effect on the expected accuracy after pruning, and therefore we went on and measured how much lower can we expect the class accuracy after pruning to be given the properties of these tasks. And we also started going a little bit deeper into the inspection of the model itself and how it behaved. So we took the QMness task, which comes with metadata about the writers that contributed the handwritten digits to this data set. And we started noticing how the model behaves differently on different demographics of individuals, after pruning especially. And after pruning, its performance significantly degrades for certain individuals, as circled one of them here, and really how this might be related to properties of the digits that the network now all of a sudden struggles to classify after compression. And so, for example, here, just one thing out of the many that we notice is that there is a significant decrease in robustness to the slantedness of the handwriting style after pruning. So that's just one example. But what's really the takeaway here? It's that we need to continue questioning our models, especially in this day and age, and we need to apply sound methodologies inspired by maybe what's happening in the sciences to continue analyzing and probing our models. And so, with all of that, what is left? What's next? So I'm really lucky. I think my work has really been able to span both curiosity-driven and application-driven angles of topics like computer vision and initialization and compression and a lot more. And I'm absolutely thankful for a lot of the strong cross-functional relationships across all the business units that I was able to form and establish at a place like Facebook with some of our AR, VR teams or on-device teams. But in my mind, there is no way in which the future won't take us closer to AI being more private, more efficient, more responsible, and ultimately ubiquitous. And to me, in a way, compression seems to be extremely relevant to all of these points. And so that's why I find research in this space so compelling. But of course, there's so much left to be done, as you've seen. So many more exciting avenues of research for efficient AI. So in the immediate future, we're looking, for example, at ways to automatically identify these lucky subnetworks that train to high performance. And this is a nascent field of research of pruning and initialization. And we will be looking forward to setting our benchmark. And then personally, I am very keen to deliver on real tangible improvements for the community to be able to leverage sparsity and compression techniques, so sparsity plus quantization perhaps, while making use of all of our hardware, so squeezing the last bit of performance out of that without wasting unnecessary cycles. And this is a very, very complicated task that requires collaboration with many experts, especially on the hardware side of things. But I think that research that is grounded in the physical constraints of challenging deployment domains has the potential to yield truly impactful, truly revolutionary results. And so compression has always been and will continue to be top of mind for other important aspects of AI, such as interpretability, privacy-preserving machine learning, as well as some of the new cool applications in AR and VR, and so much more. So with that, I hope that I was able to intrigue you enough for today to push you to check out some of these model optimization techniques that I mentioned throughout the talk, follow the research, and get the most out of your models. Thank you.
All right. I think I speak for everyone on the call right now. We have a good audience here when I say thank you so much. That was really amazing and really interesting stuff there. A few questions. We do have one here in the Q&A, and then I kind of have a separate channel going on with some of my researchers here at the Clarifai side. some questions as well. We'll take Edward Schwartz's first here, but how does the depth of the lottery ticket hypothesis sparse networks compare to previous good models? Are deep models still needed to be competitive?
Yeah, so most of the lottery tickets are obtained from state-of-the-art architecture. So we start from extremely deep networks, and most of the lottery ticket hypothesis work, as far as I understand, as far as I know, removes connections or neurons within layers, but doesn't remove entire layers. So the depth of the neural network remains whatever it is that you started out with. So it depends on the base architecture that you start pruning. So these are deep models in many ways, but they're extremely sparsified. And there are many reasons why we've shown that depth is advantageous for deep models. I don't see that going away anytime soon. There are now, even new results showing that actually width helps as well. We've always put so much effort towards going deeper as opposed to going wider. There are now very interesting results for deep and wide neural networks. So yeah, depth is there to stay, and for good reasons. Also on the theoretical side, it's just more about how do we place connections within these layers. Are they supposed to be as dense as they've always been, or can they be sparser? And these results seem to point to sparser connectivity also being advantageous in a way. Is something that we've known from biological observations as well. The brain is not a densely connected or as densely connected as some of our networks. So there are reasons for energy efficiency that point us in this direction, but then we have to be mindful of our implementation hardware as well and complications that arise from that.
Excellent. Thank you for that concise answer there. I hope that was good for you there, Edward. When you were talking about the intersection of lottery tickets, it did seem really interesting. There was some questions on our end through our kind of back channel. What is that? What does it mean if you're able to find these intersection data, the tickets, and are we learning something about the way the models are learning that's useful moving forward? What's going on there?
Yeah, so that's kind of the holy grail. I don't think I can claim that we're already there and having understood really what the significance of this is. So far, it's mostly an empirical observation that these intersections do exist. There is a core part of the network that seem to be always necessary to solve the task in terms of how it contributes maybe to feature formation, but what exactly it's doing and why it's important and why it goes in prunes and why do those weights and not others evolve in such a way as to always remain in prune based on our pruning techniques. That's not quite clear yet. So as I said, this is very much a work in progress that I'm presenting right now. So we will be striving to find an answer to this question, and hopefully there will be one. There will be something that we can learn from these models that is more general and generalizable than what we could have learned from any other individual type of lottery ticket, because there seem to be just so many. But maybe this one has something a little bit more fundamental to be determined that we can then exploit to get systematic gains in performance in the way we train networks.
Interesting. Yeah, it sounds like there could be some new news coming out of this.
We'll see.
A few more questions that are popping up here. Yunjin Fama, she has a question, and I kind of had this while I was listening as well. If you or anyone, maybe it's either at Facebook or any research that you know of, directly compared pruning with knowledge distillation techniques, specifically kind of teacher-student network for model compression. She's mentioning that where Yunjin is that they had some success with Bayesian MCMC distillation, but hard to scale. I think while you're answering this, just quickly for some of the people, what's the easiest way to describe the difference between knowledge distillation and maybe pruning, and then go into if you've done any direct comparisons?
Yeah, so knowledge distillation is another incredible technique that I mentioned when I was kind of giving you an overview of the entire landscape of efficient model design. And model distillation, just very simply put, consists of having a larger teacher network that learns a complex representation, that solves the task really well, and then trying to distill that knowledge into a smaller student network that, instead of learning directly from the task, learns from the teacher itself, so from its output perhaps. And there's an enormous field of research just around that and how to do that exactly. Do you learn from which part of the model, and like what should be the difference in capacity between the two, and what does this tell us about trainability in general? And usually, like, student-teacher networks can also be used for theoretical studies, and not just for practical applications. So it's a very interesting setup. And so yes, so it's another method to distill knowledge into a smaller network. Obviously, it proceeds in a completely different way. It is, once again, potentially computationally intensive as a procedure. People can do smarter things, obviously, to get around it as well. I don't know exactly of papers of results that compare in the same paper lottery tickets to knowledge distillation, primarily because it depends on what a paper is trying to achieve. So oftentimes when we talk about lottery tickets, we don't talk about them just in the sense of what's the maximum performance I can get out of my hardware, what's the fraction of reduction in flops or anything, and they're still very much in the exploratory research phase. And so we are trying to figure out what can we learn from these architectures, and can we use that insight to build more principal networks to begin with from now on. I don't know how well that fits into the description of the problem statement from knowledge distillation. Yeah, off the top of my head, I can't think of a good paper or good result or good application that compares the two. But I'm sure, within companies, people who are really interested in squeezing the most out of their networks are comparing and combining, distillation with quantization, with pruning, and more to really get the best out of these.
Interesting. Okay, that's that's a great description of differences there. Definitely something we could spend the whole session just diving into, I believe. I want to touch on, we only have a few minutes left here, but I want to make sure we at least touch on these two questions as quickly maybe as possible. I think Jeff had his question here first. Worrying about just the risk of pruning out interesting outlier attributes in data sampling when you're pruning. Is there a concept of anti-solution pattern? I don't know what WRT stands for. Pruning.
With respect to?
Okay. Yeah. So, thanks.
So sorry, like the core of the question is like, are there any anti-patterns in terms of how not to prune? Like what you should not be doing when you prune? Is that the core of the question, or did I misunderstand that?
I think you're gonna have to go with that direction on this one.
Okay, sounds good. Well, I'll take it this way, and I can follow up with people if they're interested in more. But so I think like what we've learned, what we originally thought is that structured pruning is not particularly advantageous compared to unstructured pruning, and to some extent that bit of knowledge holds in the sense that unstructured pruning seems to give higher performance. That's the same level of sparsity. So networks are more resilient to that type of sparsification. Structured pruning, where you remove entire layers or entire channels, seems to be a little bit more damaging. Now, that's not necessarily always true. Like we have shown that some structured pruning techniques actually do tend to give us like good performance, and then there are hybrid structured / unstructured techniques. So if you have a convolutional network, instead of pruning away an entire channel, you can kind of block or prune things. So you can prune blocks of your filters, and that sits kind of in between the two, but seems to be the way that people have sort of converged to get the best out of the both worlds. What not to do? I mean, this, pruning all in one shot. So if you want to prune 90% of your model, don't prune it all at once. Prune it, prune 20%, and then you can fine tune it or initialize it, and then prune it again, and then prune it again. So that seems to give us more robust results, really.
Excellent. Okay, last question was from Zach Greenberg. We're actually out of time on here. Zach is one of our research scientists actually here at Clarifai. I'll pass you along his details here to get back to him a little
Sounds great.
about ways to actually maximize efficiency for model pruning. I want to go ahead and just thank you again, Dr. Paganini, for sharing with us today. Really great stuff. And as always, I said at the top to everybody, we are going to go ahead and make this recorded session available. So it should be available within 24 hours. Thank you again, and hope to see you somewhere around in the rest of the sessions today.
Thank you.
Have a good one.